Hello everyone, welcome to my today's presentation. The title of my presentation is Impacts of Equivalent Dynamic Grid Impedance on Inverter-Based Resources Plant. I'm Himadri Shekhar Das and my other co-authors is Dr. Shuhui Lee and Bing Lu. We are all from the University of Alabama Electrical and Computer Engineering Department. Nowadays, the distributed generation units such as solar photovoltaic, wind turbine, EVs, and energy storages are connected to the grid using the inverters, grid-connected inverters. They are called actually inverter-based resources. Now, with the increased number of solar of inverter-based resources, nowadays they are connected to the grid as a group. So this group, where like hundreds of IBRs are connected to the grid at a single point of interconnections, they are called IBR plant. Now, when the IBRs are connected to the grid as an IBR plant, recently there are several event occurred. They are called like abnormal operations, such as generational loss and IBR unstable operations, sometimes tripping of the IBRs. So the Texas Electric Reliability Corporation has reported some of these events, and the Hydro One networks in Canada and some organizations in China, they reported it. They find out the reasons, like they assume the reasons are the weak grid conditions and the interactions of IBR power electronics with the series compensated transmission line. To analyze the system, the most important parameter of my study is the equivalent dynamic grid impedance. It's the modified version of dynamic grid impedance. Why I call it equivalent dynamic grid impedance is like when an IBR plant is connected to the grid, the dynamic impedance varies based on the number of IBRs connected to the grid. So So you can see the circuit here. Imagine it as a multiple number of units. Like when multiple number of units is connected at the point of common coupling, what happens here is the current injected to the grid, it multiplies. So the impedance, the LG and RG, it also changes. In plant structure, the grid strength is represented by the composite short circuit ratio. It's represented by this equation, the short circuit MVA power divided by the total rated capacity of all the IBRs. Okay. So and another thing, the equivalent dynamic grid impedance, it can affect the IBR plant for different kind of filters differently. So for it, here I showed only the LCL filter, but I analyzed it for L filter, LC filter, and LCL filter. So this is my setup. Here I have some assumptions such as all the grid grid connected, all the IBRs, they are in grid following mode, not in grid forming mode. And the current sources, I represented it as a all the IBRs, I represented it as a current source because the current source units contain the fundamental and the harmonic components, and as they are they are putting currents into the grid, so it can be represented as a current source. Okay, so and all the IBRs, they are connected to the grid as a plant structure, obviously. And the parameters I varied to see the impact is the type of filter, number of IBRs, and also different grid strength to see like in which structure the effects are like more severe. Okay, so for the grid strength, the composite short circuit ratio, if it's less than 2, it's a weak grid. If it's greater than 3, then it's a strong grid. So I chose 3 values: 1.5, 2.5, and 4.5. So to represent it as a 3 different grid strengths. Okay. So the results I find out here, it can you can see it's 3 columns represent 3 different short circuit ratios, 3 rows represent three different type of filters, and each of these lines, they represent the number of IBRs. For an example, the green one is 1 IBR, the blue one is 100, red one is 300, and black one is 600. So if we analyze these results, you will see that for the L filter, there is no notch. That means there is no resonant frequency. But with the increase of the IBR, the magnitude of this frequency sweep lines increases. That means for the higher number of wind turbines, the harmonics, the magnitude of the high order harmonics, it's higher for the VCC voltage. Okay, so then for the L and LC filters, they have the resonant frequency, and as the number of number of IBRs increases, the resonant frequency drops to lower frequencies. That means if the number of IBRs is very high, then it can interfere with the IBR controller crossover frequency. Then if that happens, the IBR controller stability will be compromised. So that is a major reason of disconnecting the IBRs from the grid. Now, as we can see, with the increase of number of IBRs, the equivalent dynamic grid impedance, it changes. That means it actually increases. That means the grid strength, the short circuit ratio, it decreases. So that means if it's for a strong grid, the number of IBR is increasing, and then the equivalent impedance it's also increasing. So the grid strength decreases. So it can convert from strong grid to weak grid actually. So let's see what happens if the grid strength, the dynamic grid impedance varies and the grid strength changes. What happens? So let's analyze the results from first column to the third column. Okay. So for we will be able to see the variation more for L and LC filters, not for LC and LCL filters, not for L filters. So there is an assumption when we design the inverters, that is we can allocate the impedance values mostly for maximum for 10% of design value. So if the dynamic equivalent grid impedance changes, it can vary more than 10%. Then what happens? The controller design, it will not hold up for those kind of changes, and it can lead to unstable operation. Okay, and this happens for LC and LCL filters mostly. And another one is already I explained that the resonant frequency, as the short circuit ratio drops, the resonant frequency for LC and LCL filters, it gets closer to lower values. If you can see, for the 4.5 CSCR, the maximum for maximum number of IBRs, the resonant frequency is at 2 kilohertz, but for 1.5 composite short circuit ratio, is at 1 kilohertz. So that means it's getting lower, and for this this can interfere with the IBR controller crossover frequency, and also can lead to IBR abnormal operation, such as losing the stability. I can summarize the results here. The changes in grid impedance can heavily impact the operation of and reliability of the IBR systems, and the impact even magnifies and can lead to unstable operation, and even cause IBR tripping when the equivalent impedance fluctuation becomes large. The major effects are voltage fluctuation at the point of interconnection, excessive harmonic injection, and the stability of IBR control mechanism. The main reason for the impedance fluctuation is the variation of number of IBRs in the IBR plant and the variation in the current injection amount to the grid. To solve the problem, advanced control mechanisms and the grid integration mechanisms are needed to be developed, which can address these issues presented here. Thank you very much for paying attention and have a great day.